In this section, we will talk about the requirements on the analog to digital converter and a direct conversion receiver in an OFDM system. There are many factors that go into determining the number of bits that have to be used for the ADC. Here we show the block diagram of the RF front end. Basically, the signal is received. We go through the low noise amplifier. We mix the signal down to baseband. Here we show we're going through two analog filters, and in between we have a variable gain amplifier which is controlled by the AGC signals coming from the baseband. The baseband analog filters do not completely filter out adjacent channel. That is the job of the digital decimation filter, which can implement a filter with a large attenuation and a short transition band, whereas if the requirements on the analog filters were to eliminate the adjacent channel, then the analog filters would consume a lot of area and power and would be very difficult to match. Whereas in the digital domain, we can implement the decimation filter with bounded complexity in order to eliminate the adjacent channel. Therefore, the analog to digital converter has to take into consideration that the signal that it receives can have the desired in-band channel and a large adjacent channel component which could actually dominate the in-band channel. There are a lot of factors that go into determining the requirements on the A to D, but before we get into those, let's review how an analog to digital converter actually works and derive the expression for the signal to quantization error. Here we have the transfer function between the input analog voltage and the digital code, output code of an analog to digital converter. This ADC will have a quantization error, and the error would span between minus delta 2 and plus delta 2, where delta is the step size. So for an input voltage, for example, over here, in this case for this particular voltage, we have an exact digital representation. However, for this range over here, we get an error because it is all mapped to the digit 101. And around this exact point, we will have plus delta 2 and minus delta 2 possible errors. And typically with a analog input, which is very exciting, which is what we will encounter in OFDM, the probability distribution of this error would be uniform. That is, there's an equal chance for the error to be anywhere between minus delta 2 and plus delta 2. So if we look at this diagram here, we have a plot of the quantization noise PDF, or probability distribution function, and we know that the error will never exceed minus delta over 2 or plus delta over 2. It's bounded within this region. And we also know that it is uniform in the sense that the probability that the error is any number in between minus delta over 2 and delta over 2 is the same. And of course, for a PDF, we require that the probability that the error occurred is 1. So if you integrate over the PDF and require that it equals to 1, then we get that the amplitude here, the value here for the PDF, is 1 over delta, so that the total area is equal to 1. From this PDF, we can calculate what the variance of the quantization error is, and we get that sigma sub q squared is equal to delta squared, delta to the power of 2 divided by 12, or delta squared divided by 12. This is easily computed by integrating the PDF with x squared. So now we have an expression for the variance of the quantization noise. We are interested in what the signal to noise ratio or signal to quantization error is in the case that we have a sinusoidal input. Here we show a sinusoidal input that ranges, which is full scale, that goes from the maximum to the minimum analog voltage input range. So it's a full scale. And what we're interested in is, for this particular sine wave, which we have quantized, what is the signal to quantization ratio? The definition of the signal to noise ratio or signal to quantization ratio for full scale is as follows. The SNR is equal to the power of the signal divided by the power of the noise, which is just sigma squared sub q. The quantization noise power is its variance, which is delta squared over 12, which we derived earlier. The power in the sine wave is its full scale amplitude. So you take the full scale and divide it by 2. So if this is the full scale, we divide it by 2, we get the maximum amplitude. So we take the full scale amplitude divided by 2, divided by the square root of 2 to get the RMS value for the sine wave. We square it, we get the average power of the sine wave. So this is the power of the signal, and this is the quantization noise. Now the full scale itself, if we go back to this diagram, is equal to the number of steps times delta. So here we're showing an 8-bit quantizer. So we have a total of 2 to the 3 or 8 levels, and the width of each level is delta. So the full scale, 2 to the n times delta, divide that by 2, we get, of course, the amplitude of the sine wave and the RMS value. If we simplify, we get that this expression boils down to 2 to the power of 2 to the n times 12 over 8. Of course, the delta squares cancel out. If we compute the signal-to-noise ratio in dBs, we take 10 log of this expression over here, then of course the exponential 2n comes out, and we get 2 times 10, 20, with the exponential n times log base 10 of 2 plus log base 10 of 12 over 8 times 10. This number here just turns out to be 6.02, or just 6, so this becomes 6n plus this number here, which is 1.76. So this is the expression for the signal to noise ratio for an analog to digital converter in the case that the input is a sinusoid. If we have an arbitrary input, then we need to specify for that arbitrary input what the peak to average ratio is. The reason for that is when we make the definition for the signal noise ratio, recall that it is the ratio of the average power divided by the quantization noise power. And the average power can be defined in terms of the peak to average ratio. In the case of a sinusoid, the peak to average ratio is 4 square root of 2. But in general, if we include the peak to average ratio, we get the expression for the signal noise ratio, which is equal to 6n plus 4.76 minus 20 log of the peak to average ratio. Now it turns out that for a sinusoid, the peak to average ratio was over the square root of 2, and if we plug that in, we get minus 3, we get 3 dB. So that's where we get for the sinusoid that the signal noise ratio is 6n plus 1.76, as we derived over here. But in general, we would take 4.76 and subtract from it the peak to average ratio. So in specifying the requirements for the analog to digital converter, we always have to be aware of the peak to average ratio for the particular signal. In the case of OFDM, OFDM has a large peak to average ratio, and we can assume that it's anywhere between 6 and 10 dB, and we will usually take 10 dB for the worst case. I will now discuss the dynamic range requirements of the ADC for 802.11a. Purpose here is to come up with exactly how many bits do we need for the analog to digital converter in a direct conversion RF front end, and using OFDM as specified by 802.11a. Here are some of the factors that affect the ADC dynamic range. Our objective is to determine how many bits we need for the ADC. In order to derive the dynamic range of the ADC in terms of the maximum input power level and the minimum, we refer to the standard. So here we see that the standard reads that the receiver shall provide a packet error rate of 10% at a packet length of 1,000 bytes for a maximum input level of minus 30 dBm measured at the antenna for any baseband modulation. So the maximum input power is minus 30 dBm. So referring to the receiver performance requirements, we see that at 6 megabits per second, the minimum sensitivity is minus 82 dBm. That is, at an input level of minus 82 dBm, we should achieve a 10% packet error rate with packets of 1,000 bytes. Now, usually quality products would exceed this requirement, but for now, we see that the input ranges from minus 30 dBm at the maximum to minus 82 dBm at the minimum. So if we take the difference, the dynamic range is equal to 62 dB. So an analog to digital converter would have to accommodate for this wide dynamic range. And we would have to allocate a large number of bits in order to accommodate for this dynamic range. However, usually we would employ automatic gain control, where we start out with a very high gain, and if the signal to noise ratio is large, then we start peeling off the gain, reducing the gain through feedback from the baseband to the analog RF front end, controlling the variable gain amplifier. So the AGC assists quite a bit in terms of relaxing the requirements on the dynamic range and reducing the number of bits that we need for the ADC. However, we still need to allocate bits in the ADC to accommodate the stepping in the AGC, where the variable gain amplifiers, for example, may be stepped in steps of 2 dB in order to control their gains. And we will cover that in the later diagrams. So in general, you have to accommodate a wide dynamic range, but with AGC we can relax the requirements on a number of bits required for the ADC in 802.11a. Another important parameter is what is the signal to noise ratio that we need to support. That is the total signal noise ratio including interference. So at 54 megabits per second, we require a signal to noise ratio roughly around 20 dB. This is the signal noise ratio at the minimum sensitivity point. So if we look at 54 megabits per second, the minimum sensitivity point is minus 65 dBm, and this translates into a signal noise ratio roughly around 24 dB. The constellation shown here is the received constellation at 54 megabits per second at the sensitivity point with a signal noise ratio around 24 dB. Now the ADC is going to add quantization noise to the noise already present, and in order to meet this specification we will require that the quantization noise be at least 10 dB below the noise shown here, associated with the noise figure and interference and other nonlinear effects that are in the receive chain, the total noise and interference. So if the signal to noise ratio is 24 dB, we require that the quantization noise be 10 dB below the noise, and therefore if the signal noise ratio is 24 dB, we need the signal to quantization noise to be 34 dB. So we want the quantization noise to be 10 dB below. This is a major factor in determining the requirements of the number of bits required in the ADC. You have to relate it back to the minimum sensitivity point and the required SNR. Another important factor in 802.11a or OFDM in general is the fading characteristics of the channel, and we can show this in this diagram here. When you have automatic gain control, the AGC algorithm works such that a target RMS value is met at the input to the ADC. So if the signal is too high and we're in saturation, it will peel off the gain and reduce the gain so that we meet the target RMS value into the ADC, and otherwise we increase the gain. The AGC algorithm operates on the short preamble in order to adjust the AGC, because once the AGC has been set, we are not allowed to change the AGC throughout the decoding of the packet. That is forbidden. So once we adjust the AGC, the final steps of the AGC, we freeze it. The AGC is no longer adjusted. Therefore, the AGC is always performed on the short preamble. The AGC achieves our target RMS into the ADD based on the short preamble. However, that is done for the data portion of the OFDM signal. So it is important to understand the relationship between the RMS value of the short preamble and the RMS value of the data part of the OFDM signal. When you don't have fading in the channel, they track very well. So there's a high correlation between the RMS computed with the short preamble and the RMS computed in the data portion of the OFDM packet. However, as this diagram shows, when we have fading, multipath fading, different channel realizations result in different relationships between the preamble RMS and the data RMS value. So in the simulations we show here, we have 10,000 channel realizations, at 50 nanosecond RMS delay spread for the channels. We're showing the computed value for the RMS preamble. We plot that on the x-axis, and we plot the associated RMS value for the data part on the y-axis. So each point here shows what the RMS value for the preamble was and what the RMS value for the data portion was. We see that in general we follow a curve, whereas a RMS value computed for the preamble correlates with a larger RMS value for the data, which is good. That's what we want. However, there's a lot of variation here due to the different channel realizations of what the multipath fading channel does to the signal, such that the RMS value of the preamble does not predict the RMS value of the data as accurately as we would like. So this ambiguity in computing and relying on the RMS of the preamble in order to predict the RMS value of the data part due to the fading multipath channel has to be taken into consideration. So from this curve we can see that there's almost a 5 to 7 dB variation here that we need to account for. That is, if we lock on the RMS for the preamble, then we need to allow for 5 to 7 dB possible discrepancy with the RMS value in the data part. So we would have to take that into consideration and coming up with the requirements for the analog to digital converter's dynamic range. Another factor affecting the dynamic range of the analog to digital converter in OFDM is the adjacent channel. So as we show in the diagram here, and we discussed previously, the adjacent channel could have a very large power compared to the in-band channel, the desired channel. If we go back to the table here for the minimum sensitivity, we see that at data rate of 6 megabits per second, the adjacent channel could be up to 16 dB higher than the desired channel or in-band channel. Here we show a portion of the circuit for the demodulation of the received RF signal back to baseband and performing the analog to digital conversion, the sampling and conversion to analog from analog to digital, followed by a decimation filter. The analog filter in the RF front end does not adequately filter the adjacent channel, and as we've pointed out before, this has to do with the fact that if we require that this filter be very sharp and be able to suppress the adjacent channel completely, that would result in a filter with a large area, more power consumption, and of course it would be very difficult in the analog domain to have balance between the I and Q channels with such a filter. It is more appropriate to do the filtering in the digital domain after the analog to digital conversion, since we can implement the decimation filter in the digital domain with less complexity and completely eliminate the adjacent channel. You will always have some aliasing, as we discussed before. The point that we need to consider about the requirements for the analog to digital converter is that due to the relaxed filtering on the analog part, the signal after filtering may contain a large component due to the adjacent channel. In fact, the adjacent channel could be larger than the in-channel signal. Now the decimation filter will filter out the adjacent channel such that we do meet our requirements, but the point is that the analog to digital converter's dynamic range should accommodate the adjacent channel so that the decimation filter can eliminate it, and then we recover the in-band channel. This means that we need to allocate some bits in the ADC in order to accommodate for adjacent channel, and this is roughly going to be about 6 dB that we need to allocate for adjacent channel. So keep this in mind. The automatic gain control algorithm, of course, reduces the dynamic range requirements on the ADC considerably. However, the AGC itself has a discrete number of steps used for controlling the gain of the variable gain amplifier. And typically the step size for the variable gain amplifier would be anywhere from 2, 3, 4 dB, typically 2 dB. so that we need to take into consideration the fact that the AGC will not be able to produce a gain that would precisely match our target RMS. So we allow for 3 to 4 dB for the issues involved with the dynamic range of the AGC and the AGC step size. So this table summarizes the results that we talked about. First of all, we had the effect of the AGC on the preamble, the fact that we locked the RMS value of the AGC locked on the preamble in order to predict the requirements for the data portion of the OFDM packet, and we saw that because of multipath fading, we need to have a budget of 5 dB for that. We allocated 6 dB for adjacent channel and about 4 dB for the AGC fine and stepping. We mentioned that at 54 megabits per second the signal noise ratio was 24 dB, and we needed to be at least 10 dB below that with quantization noise, so we need 34 dB here. The peak to average ratio we will use for OFDM is 10 dB. So if we add all this up, our signal noise ratio for the ADC comes out to be 59 dB. And if we plug this into this equation here, ignoring the peak to average ratio since we've already used it, then we subtract 4.76 from 59 and divide it by 6, and we come up with 9 bits as the requirement for the ADC. So this example is almost right on target if we look at the published papers on OFDM and ADC specifications. Some papers actually use 10 bits.